you, Fred. Hello, my name is Leonardo. I'm a researcher at Flashbots, and here with me are Mo, Fred, and Mateus. Also, a few more members of our team and some friends that we invited for this session. At Flashbots, we have been doing an exploration of hardware for secure execution, and today we're starting a series of sessions where we want to share openly what we have learned, the challenges we are facing, and the experiments we are planning for the future. So today we will have Mo giving us an introduction of Intel's SGX, which is a trusted enclave for the secure execution on machines that are not trusted. And this is interesting, right? This will showcase some of the challenges that we have to accept for where we are now in the available technology and where we want to get in the future. At Flashbots, we have been doing research on the flows of economic we have been doing research on economic flows and how this usually tends to align in a hierarchy. People with more information will get more money, and with more money, more information, more power, and that will continue growing. So we have introduced protocols to observe this, to modify some of the equilibrium on these information flows, economic flows. And currently, we are working a lot on this separation of the proposer and builder of blocks in a blockchain. For the current design, we have to trust a relay, an intermediary on this economic flow that both the proposer and the builder trust. And this is not where we want to get. So we're exploring these technologies, these secure enclaves, and maybe that will allow us to not trust the relay. But with the current way things are, that will mean trusting the hardware designer, the hardware manufacturer, in the case of what we will see now, Intel. And it will we will have to trust the cloud provider where these machines are running, for example, AWS or Azure. And that's an interesting trade-off that we are exploring and hoping that will open new ways, will open places for a solarpunk future where all the hardware is open, all the designs are open, and everything that we have to execute will be verified. Let's see how we get there. Thank you, Mo, for the time. Thank you, Mo, for sharing the knowledge. Would you like to introduce your role in Flashbots, your team, and what are you currently focusing on?
Yeah, definitely. So thank you very much, Leo, for the nice introduction. Can you hear me? Just to check. Just a thumbs up.
I can, yes.
Awesome. So yeah, I'm Mo. I recently joined Flashbots as mainly for the role Intel SGX engineer, so the TEE part. So my team, I work with a team that consists of Mateus and also other two colleagues, Frieder and Andrew Miller, and we mainly work on, like as Leonardo mentioned, we work on the security part where we want to use or utilize the TE in our product to see how we could profit from them and improve the security for our products and so on. So you probably are familiar with some of the products that we have been building on top of SGX, and we have written some blog posts on and we shared them also in the SGX TE blog post that I recently written. And today is going to be one of like the kickoff session of a series of sessions that we are going to do in the future in the TE section. But yeah, today is going to be more or less like lightweight version. where we are going to introduce Intel SGX, and then we'll have then the agenda will be like very lightweight. So first we will take a look 10 minutes on Intel SGX, what it is, its limitations, how it works. And then we will have a hands-on session where we will look at the code section. How would you run, like for example, a Hello World version, and then we will incrementally build on top of it a little bit just to play around and show you around what you could do. And then we will leave like at the end also like 10 minutes session where like for questions and answers. Of course, if that's not enough, we can later on do this asynchronously. So you can reach out to us and we'll try to answer most of the questions, but as much as we could. All right, so we will start with directly straightforward with what is Intel SGX. And Intel SGX is a hardware security feature that Intel provided in their Skylake architecture in 2015. So they extended the instruction set in the x86 instruction set with new instructions that allow the creation of security compartments, the so-called enclaves, that runs your security sensitive code inside of them. So it's a part of your application, as you can see here. And basically, everything that runs inside the enclave is considered trusted and everything else is untrusted. So the threat model here is quite strict. So it protects against a malicious hypervisor or host from tampering with the data, and even protects the confidentiality of this data inside of it. And those enclaves reside in processor reserved memory area, which is called the EPC, the enclave page cache, and it's encrypted by a hardware unit, the memory encryption engine, and then later on with the scalable SGX. It's using a different technique called total memory encryption. So now I mentioned the scalable SGX. Initially, it started for the server and client side, but then with the advancement of the technology and a newer version, they shifted only to the server side. So the production for the client side stopped there and they continued on the server side. So as you can see here, it reduces or minimizes the trust down to the CPU package. So basically the CPU firmware and the enclave code. And you can think of a quite like a set of use cases that you can use it for. For example, if you have, let's say, an auction where many people are sending bids, like an auction service, and these bids needs to be like secured until the results come out. So you don't want these bits to be visible or being tampered with, or even like a curious host can look into them and basically do like some kind of malicious activities by bidding slightly above and then win the auction and so on. And then you would put that application inside an enclave where the computations happen there, the bids will be sent there, and then once the results come out, you can make sure that nothing was being tampered with. So this is one of the technologies that is now called one of the trusted execution environments, the TEEs, among many others. Maybe you have heard of AMD SEV and Intel TDX recently, and ARM Trust Zone, Risk Keystone, and so on. So now we will only focus on Intel SGX. And since I mentioned this EPC where the enclaves reside, let me slightly explain to you what this EPC is. So we mentioned that it's the chunk of the memory which is reserved for the enclaves to reside in. However, it consists of multiple structures. So a chunk of it goes to the Merkle tree, and this Merkle tree, purpose is for the integrity protection, to make sure that the enclave pages haven't been tampered with and to ensure integrity. And then we have the enclave page cache map, which contains like the permissions to the enclave pages and like the mapping to those enclaves that reside inside of it, which we'll see now. And then the rest here, as you can see, this is, for example, the one enclave and what one enclave could consist of. So one enclave could consist of, or consists of the SGX enclave control structure, which contains the enclave's metadata, such as its size and so on. We will see on also later. And each enclave consists at least one thread control structure, or also many. to define the multi-threading inside the enclave, and the amount of threads that can go simultaneously inside the enclave, and the entry points and so on. And each thread control structure will be assigned a state save area. And the state save area, basically, it's for each thread control structure, it defines the place where it stores the CPU state in case of an asynchronous exit events or even synchronous exit events that happen for the enclave to go to the untrusted world and so on. And then, of course, we have for each enclave the stack and heap, which is in the SGX version 1. They are of a fixed size, which you predefine. So they have a fixed size at the start. But now with the SGX v2 and new instructions came to play, the enclave dynamic memory management came into play here. And then you can define basically a minimum size for both of them to start the enclave with, and then maximum heap size and stack size that they can dynamically increase up to at runtime. So this is just for the ease, but they are still limited in size based on a pre-configuration that you set beforehand. And then, of course, the text and data, the code inside the enclave. All of these structure from here till down here, they define the measurement enclave. So what's the measurement enclave is? This measurement over the enclave means is basically the hash of the code of that enclave. And this hash will be used later on, as we will see later on, for the remote attestation to make sure, as a user that is sending data, sensitive data, or executing sensitive functions or security critical functions inside the enclave, can use this measurement first just to make sure that it's running the correct enclave, not being tampered with, and so on. So yeah, this is the EPC. It's encrypted at all times, so at ease, during transition, and during execution. And initially it was limited by size by 128 megabytes, and then recently with the scalable SGX, they increased it up to 512. Yeah, we talked about the confidentiality and integrity of it. And up to the point where the enclave has been created and initialized, there shouldn't be any sensitive data inside the enclave code. So basically, because it's inspectable, and then upon its creation and execution, everything that then happens, then it's confidential and secure and integrity protected. So don't put any, for example, secret keys inside the enclave beforehand, or you can basically transfer them through like trusted channels and so on. So yeah, we mentioned attestation. So attestation is a process, or remote attestation is a process that Intel provides for the Intel SGX to guarantee to the users or the service, like the service providers, like when you deploy your application in enclave, to give you the guarantee that your code is running on an authentic SGX machine, running on, for example, the recent security updates are there, and that your enclave is not being tampered with by checking the measurement enclave and so on. And this is called the TCB, the Trusted Computing Base. So the Trusted Computing Base contains data that some of it are mutable, such as the platform software and CPU firmware, because the CPU firmware can be updated to add protection against side channel attacks that happened on SGX before, for example, Spectre and Foreshadow. And it also contains also like mutable optional policies that you can set optionally, of course. And there are some data that are immutable, such as the CPU logic, of course, and the enclave measurement. So the enclave measurement is immutable in this case because after you create it, you would expect it not being tampered with, because once it's being tampered with, then the enclave measurement will change. And then you would expect it to be immutable when you are running your enclave. There are two versions of attestation here. They initiated it with the EPID, the Enhanced Privacy ID, which is going to be deprecated soon and replaced by the DCAP, Data Center Attestation Primitives. Just to show you like a short example of what the DCAP does. It's very similar in the structure of the EPID. However, the change here is when Alice receives the quote. So we have this quoting enclave similar to the EPID, and instead of provisioning enclave, you would have provisioning certificate enclave. So upon the initial deployment of your SGX application or SGX machine, the provisioning certificate enclave would have to do this only once to contact the enter provisioning certificate service to get the list of certificates, the registry once, and then it will be embedded here in this enclave. And then upon each remote attestation request that come from a user or like service provider to the SGX app, the quoting enclave will create a report, then uses the provisioned keys from provisioned certificate. So it uses the public key infrastructure to create then a quote, and then it sends its quote back to Alice. Alice, in the original version of EPID, it sends this quote then for verification to the enter attestation service. But then this will be replaced by a different way. So for example, Alice could now send it to a third party, verifier party, which periodically fetching and updating the cache certificates from the PCS. Or Alice can do it herself, basically by having the certificates somewhere like cached, and then does the verification itself, like looking at the measurement and the rest of the code. And if that's looks good, then it can send them basically or execute the security critical data or functionalities. Yeah, so this is briefly about the attestation. So now regarding the programming models, how would you program your application to become like SGX aware? And initially, you could basically use the Intel SGX SDK. So Intel provides an SDK for development, and basically the developer would think of a way to basically separate the application during the architecture phase of the development, separate the application into a trusted and untrusted side. So the trusted would be basically the enclave, and the app untrusted side would be other functionalities that are not necessary to be run in a security critical way. So they are not really critical. And then, of course, developer should, so from the developer perspective here, should also provide an enclave EDL file, so enclave definition language, I think, where it defines basically the interface of the how to enter like the equals and locals. So that how to enter the call functionalities inside the enclave, and in case the enclave needs some data from the outside, then define some locals. So this is kind of like you can interpret it as the interface with the outside world. And then, of course, you need to also define a configuration file that specifies the metadata of the enclave. So basically, number of like the TCSs, number of threads, enclave size, the heap and stack, the Intel software version, and so on. You could see all this data in the blog post that we wrote about this. And then there's here an intermediate step where it's called SGX Iterator. So this is one of the tools that SGX SDK offers. And it generates then, let's say, a wrapper code that will be basically used by your app, like an untrusted side and a trusted side, to traverse the function control flow. It will look like this. Basically, when your application untrusted side calls a critical function, an equal to the enclave, what from the perspective of a developer, it would look like it's a simple function call. So basically, we are just calling functions on the enclave. But in the background, it's doing much more than this. The equal critical function here is basically calling a wrapper code here in the enclave untrusted that was generated by SGX Iterator that does args, marshalling, copying, and so on. And then it passes it to the library SGX untrusted runtime system, which does the SGX equal. This SGX equal basically does the context switch and the switching to the enclave mode, the trusted mode. And then it will be then fetched by the library SGX trusted runtime system, and which in turn calls also like the generated function to the untrusted side here, which does the arguments unmarshalling, and then traverse the execution to the real function that you really intended to do inside the enclave. So as you can see here, much more is happening in the background, which describes why there is some kind of performance hit here a little bit when you do some context transitioning from the untrusted to the trusted. And then the OCall, basically when the enclave does execution the opposite side, then it will follow almost the same process here. So this is in general, like how would you develop your application using the Intel SGX SDK? As you can see here, this would require a lot of like restructuring to your like your legacy application. So it might be too expensive. So there are other solutions here in order to bring your code much faster to the market inside SGX. So the other solution would be here is basically to use library OSS. So one of this library OSS is Grameen, which we will take a look more into details now in this presentation. And library OSS in this case would basically offer like a wrapping library OS. So it's a wrapper that allows you to run your binary inside of it, and it abstracts for you all the system calls that your application would basically call to the outside, to the untrusted side, and then sends the results back in. So in this case, it would run all your application or all your binary inside the enclave. So there will not be separation where you say, okay, this part is untrusted and this part is trusted and so on. So in this case, from the developer perspective, you would have your application binary. And then what you only have to do is to write your app manifest file. And in this manifest, you would define the metadata that you need, for example, the enclave size, and the amount of threads that you need, and basically the files that are necessary to be accessed from your binary, and mounting paths and so on. Grameen tools provides like several tools for generating your app manifest SGX from the template that you write, and also there's a Grameen sign where it generates a signature for your application and that manifest, which basically will contain the measurement. We will also show you now on the hands-on how that looks like. So of course, the Grameen or library OSS in general, they have pros and cons, similar to what we saw now in Intel SGX SDK. Their major pros here is basically it's the minimal effort. So we don't have to do too much work restructuring and refactoring in order to make it run SGX. So yeah, it allows you more flexibility. And the cons here, basically, it increases the trust computing base because as you can see here, earlier we had in the application only the enclave was trusted. And in this case, we are trusting the whole application. So more code is now going to be trusted. So it will increase also the attack surface on your application in case it contains some vulnerabilities. And of course, Grameen also, it's like a development in progress. So the support for some system calls still like is limited or partially implemented. So to my knowledge, currently in their website, it says like 170 system calls are implemented from 360. So it's still in progress, but in case your application requires some unique system calls that are not implemented yet, so this would be a limitation in this case. Of course, there are other codes that you can read about in the blog post. So I think enough now for the theoretical part. So we will switch now to the coding part, and then we will have a session for your questions. So let me switch a screen to the coding part. I hope you can see it. So I already assume that you have an SGX machine already there. Like basically you can use one from the Azure, or you have one like locally if you have a rack server there with SGX capabilities. But assuming that you have a SGX machine or a virtual machine from Microsoft Azure, and you can basically follow the guides from the Grameen how to install it. It's pretty much straightforward. And once you install it, you can download their Git repository or like clone their Git repository, which I did here specifically to this task. And they have some examples here. So I will take their Hello World example and we will look closely together into it. And then we will build on top of it a little bit just to play with the manifest and have a clear view. So the Hello World is just simply Hello World here, as you can see. And
Can
the
you make
manifest
it a little bigger, Mo,
yes,
please?
definitely. Let me make this. Is this better or should I zoom in more?
I would like a little more, little
right.
blind.
No worries. Is this better?
Yes,
No, awesome. Thanks for that. All right. So let's look at the manifest that we just talked about. So since we now have this code, we can compile it into a binary, just like, let me see here. We go to the CI example. Sorry, I didn't go to hello world, and we can compile the hello world, and then we have a hello world. So we have this binary. How would we run it now into SGX? You have to write the manifest. And the manifest would include basically the first three parts here are basically the entry point for the library OS that we are using. So if you have a library OS implementation of custom implementation, you can use it here. But for now, we are using the Grameen library OS that they provide. But if you have another one that you trust, you can also use it here. And then you have to define the entry point for the library. So basically, Grameen, what it does here when you execute Grameen, it executes the library OS first, where it does like the whole setup first for you. And then this library OS entry point will basically what the library OS will do to execute the code, the binary. So you define here the binary that you want to run inside SGX. And then the library OS, after its configuration and creation, it will then execute your code inside an enclave. Yeah, here you can define some like the log level, and as you can see here, this notation it means that you are passing here you're passing environment variables or basically variables that you are passing through here in the makefile. As you can see, you can pass them like this. So when you are generating Grameen manifest, you are passing them like similar to the makefiles when you are passing some variables inside Grameen. So we are passing here the log level and yeah, defining the loader library path in this case. And what's important here is basically this part. So you can set the SGX debug mode and enable the enclave dynamic memory range that we were talking about if your machine supports it. And the file system mount is basically mounting the paths that your application would need to access during runtime. We'll have an example about it right now, but for now, yeah, let's leave it at that, just for the sake of like showing what the manifest is for now. And the SGX trusted files, those are the files that you need to define that are considered as trusted. So upon creation of the Grameen manifest file, SGX, it will take those, create the hash of them, and they will become a part of the measurement of the enclave. And this will make sure that these files have been added during creation time of your enclave and haven't been tampered with as well. You can think of it, you can make, Grameen also provides serialized, for example, argv is serialized. So argv is serialized to you basically if your application requires to be passing arguments to it at the startup, you can serialize these arguments using the Grameen argv serializer. And then there are, in the manifest syntax, there are some syntax that you can write to provide a path to that Grameen, like the serialized argvs. And then basically you can add them as a trusted file here. And then they will also be part of the measurement. So you can make sure also your enclave or application has been run inside the enclave with the correct arguments and not being tampered with the arguments that have been passed to it. So yeah, also SGX provides different syntax that you can look into. So the syntax is quite large and many features that can be used. Even the FS mount system here, if you don't define a type, it will use the change directory. Like you can define here a type, which normally goes to like this one, but there are other 4 types. The untrusted shared memory, the encrypted one, where you have to provide the encryption keys in a different way. So basically these mounted files will be mounted already encrypted, and then they will be decrypted only inside the enclave or your application. And there is the tempfs. The tempfs also, as we will look into it, also we can, if you have time, we can play with it a little bit. You can define here a tempfs where basically it gives the application a path where any file or like any file that has been written to that path will be only created during the enclave or application runtime. And once the enclave is terminated for any reason, then it will not be there. It will be deleted immediately. And if the host system tries to inspect what's been written to that file at that time, it will just be encrypted form and it cannot inspect it. So it's confidentiality protected as well. But for now, let's just at the start compile this and run it, and then we can build on top of it and have some clear view into it. So when you compile it, you have to set SGX to 1. And then as you can see here, it will create the hello world manifest SGX based from the template that you defined. And with all the files that you added in the trusted files, SGX trusted files, with their hashes and so on. And it will generate as well in the make files also the hello world signature, which you can look at by doing SGX signature struct view. And you can say hello world signature. And then you can see here the attributes here where you can see the measurement enclave. And this measurement enclave will change once we change now the content and even the manifest. So let's run it for now and see what will happen. So running it like this will basically initiate the LibreOS, and the LibreOS will execute your code. And as you can see here, we have hello world run into an SGX enclave. So this is this is quite straightforward. But now let's play a little bit with it and see if we can open a file, for example, read its content, and then write into it. But let's do it step by step. So let's say we want to open a file and read its content. So, oh, okay, nice. So good thing that we have here GitHub Copilot enabled, so we don't have to write too much. All right, great. We are opening the file text in read mode. Let's read it, for example, use fseek and tell to get, tell to get the size of the file and read its content. So that's great. We are allocating the size, we are reading the size, and then we are terminating with a null termination. That's great. Maybe here we can do error checking for reading. And awesome. So basically we don't need this. Great. And then we need to print the content. And then awesome. And then we close it. Let's compile this and see the errors that we will encounter now. So we created the measurements, and if you want to run it now, you will encounter, it will say hello world, and then when it tries to open the file text, of course, we don't have the file. Let me create it. And then add some content to it. This is just a random content for the live presentation. We add it to the file texting. All right. And then now we will run it. It will still say file text not found. This is because we are not assigning it or either not mounting it or not adding it at least to the SGX trusted files. So in order to make it visible, we need to mount it and give it directions like where to find it. And in this case, we can say it's a file and it's called file txt. All right. And then we can compile again. Oops. I don't want to create too many. All right. And we can do new compilation, and then it will change even the measurement, as you can see here, because now the file is part of the measurement as well. So now if we want to run Grameen SGX, it will read the content. It will say this is just a random content for the live presentation. So this is great. Now let's try to write into that content. So we need to write some stuff into it. So let's do, for example, printf, not in the how's it called? They said it's called file. We need to say hello from within play or from within now. All right. So now we are writing to the file. Of course, we need to do this as read write now. And let's see what errors we will encounter if we run it. Now, as you can see, we will have another error. It says, this allowing create, read, append to a trusted file. So trusted files are considered not, you cannot like modify them because as we said earlier, they are being part of the measurement. And if you modify them, it will modify their hash. And therefore, it will also modify the hash of the whole enclave or whole application now. There is a way to make the file txt to be like accessible, and you can change it. But then you have to make sure then it is secure. So when you are writing stuff into it, you have to make sure like everything's encrypted and cannot be inspected from the outside, because so you have to manually take security measurements here. So you can do here something called allowed files. And this allowed file section, you can define similarly to above. You can say, let's give the access now to file.txt. I know the naming is a little bit bad. We could have named it configuration or whatever, but for now, let's stick with this. And now after we do this, you compile again, and then you run, and it can read. And it's even, if you run it again, you will see that it's already written it in the previous iteration, hello from within the enclave. You run it again, it has already written it twice, and so on. So now we are appending content into it. So far, so good. There is also a different thing that I wanted to show. Imagine your application have such thing that, for example, you want to access it based on a specific path, like say config. In this case, what would happen is you could mount this path as if it's like a normal path. So in this case, you can go to the mounting area and you can do such thing like, so in your application, the file is actually in the same folder. So there is no config directory, but your application still expects it to be under a specific path. So we just added config to the path, and then we can simply do here, let's do this here, the config file txt, and it's basically mapping it against the file txt. This way, you would be telling the manifest or the library OS to map the file on your file system, like here, directly under this path. And then now if we do make SGX and then run it again, we'll be able to read its content and basically still work. Let me just show you, if we haven't done this, it will basically, now it will tell you, yeah, the file.txt is not found, but it's actually because the path is not there. So you have to add this mapping, and it will be able to access it again. Yeah, so far, so good. There's much more syntax that you can play with. I really recommend going through their their documentation. It's very great. I can share it with you later on here, or Leo can share it in the chat. It's very nice to look at. So you can find a lot of options that you can enable here. You can enable also the thread count and so on, even the SGX enclave. There's your enclave size, and you can define like 2 gigs for the enclave size. So at the start, it will create already 2 gigs of like memory reserved just for the enclave, in case your application requires 2 gigabytes of enclave. Yeah. How much time do we have left? Did I go over time?
You have as much time as you want, Mo, but I think this is a good
Good stopping
pause.
point. Yeah.
Yeah. You mentioned a post you wrote. It is in collective.flashbots.net. It's called TEs, Fit Intel SGX.
Mhm.
So if people have more questions about this, want to go deeper, they can join there and you will be answering their questions. I have a few questions
Yes.
here
Please go ahead.
if you are open.
Yes.
Well, first, this was beautiful. I am so happy we found you and you joined our team. Your knowledge is very clear about what's going on. And this was just a very simple example. What we did was to run get
Mhm.
into the SGX Live OS
Yep.
running in Intel SGX on the cloud
Yes.
and producing blocks for Sepolia network. Is that right? Can you tell us a little more about, well, this was a lot of work to get this thing
Yes.
ready?
So we tried to run a guess, or actually we achieved running guess in IntelliGX Grameen, running even on the mainnet, not only on Sepolia. Like I personally did it on Holisky first for testing purposes because Holisky, like the database, like their state is much smaller than the mainnet state. So it's a good start to play with because you have to load the whole state potentially inside the enclave to make sure that everything is correct. Then we switched to mainnet. The major challenge there was with the state first. So the state was huge, and we separated it from the chain data because it altogether is 1.1 terabyte, and then we only took the state, which is roughly I think 522 gigabytes inside the enclave. So we had to run an enclave which is 1 terabyte of size, which is currently hitting very high limits of Grameen. Probably it wasn't intentioned to use Grameen with 1 terabytes of enclaves, which would make sense as well, like at the start. The other challenge was the Go inside Grameen. It was a little bit cumbersome to make it performant. We used EgoGo build to optimize it, but then at some random times it just crashes due to uh, now we are talking like the Go subpart inside the Grameen. So basically the memory allocation was for some reason was overbooking at some points and basically exceeding the 1 terabytes at some points, and at some other points is what was hitting some a weird error in the allocation from within Grameen and basically crashing after a long run where basically we have already loaded the whole state in the enclave, which takes a lot of time and so on. So yeah, it was like a rough process, but yeah, it's all, we will probably talk about this much more in details in the subsequent sessions that we will do, like with the feeder and the rest. But yeah, we have been experimenting with this a lot, and then it slowly took us to the direction where we are now experimenting with TDX. And so far, we were able even to land blocks using TDX consistently, and we are still working around it to make it more operationalized and so on. But yeah.
Yeah, I think it's huge to demonstrate that this is doable, it can work, and it's promising. And then friends,
Sorry, Leo, you are disconnecting, I think. I can't hear you. Leo, is it me?
develop the application with the sections that need to be run on the trusted enclave, clearly tagged, clearly separated. And the other one that we're following, which is to run the whole binary unmodified into the enclave. Currently, Get is very, it's not very modular. If we had an execution client that's more modular, like what Red is trying to achieve, would you try a different approach? Maybe some modules from Red don't have to be on the enclave. Maybe we can design this modular execution client with trusted execution in mind. Would you do it differently if you had more modularity, or would you run the entire thing in the enclave anyway?
Yeah, it's an interesting question. First of all, unfortunately I wasn't able to catch all your question because you disconnected in the middle, but I kind of got the hang of it, like what you are asking for. Like you are asking if it's the let's say get OS is more modular, would it be different? How would we do it differently, like to run it with SGX? I mean, it all I think the design, of course, ultimately, if you want the perfect, let's say the perfect design, would be basically to architect it from the start with like with that architecture in mind. Like basically, let's take an example using the SDKs. So basically, you wouldn't rely on the library OSs. In this case, basically, you are designing it from scratch, really, and looking at which parts are security critical, and then you would basically build the interfaces for to do it inside the enclave, and then basically all the rest can be done outside because it's not necessarily. This way you would probably achieve the most performant way, but it's the most also expensive resources wise because you have to do the whole refactoring from scratch if necessary. Now you are mentioning a good point. What if like now, like if the rest team is like doubling down on making their whole system modular, how would we do it differently? I have been discussing this, I think, like with Mateusz. We discussed this like a while ago. I think we were talking about like we would still probably would need a way, like for example, if we want to do the block building inside an enclave, you would still need the state, to access the state and to make sure that the state not being tampered with and so on. And in this case, I think at the moment we would still require a way to move the state in, like, and this is huge. And a good way to do it, and I don't recall it now, the details, that if we can find a way where we don't require the whole state just to build a block. Basically, you can either do a kind of prefetching or have some kind of like you pass only the state nodes that you would require, like the Merkle tree that you require for that specific block building, and make the process like doesn't require to load, like for example, this 200 or 500 gigs inside the enclave. Or maybe apply sharding. I haven't looked into that yet, if that's even feasible, but probably not. But yeah, I mean, in mind, ultimately you require like to design it from start with that security in mind. Of course, we could use the library OSs just to like a faster way to do it. If we can just use some modules that we think should be inside an enclave, we can do this as well. If we have these modules, would be great to have as a starting point, like as a let's say as an intermediate point, like a middle solution between not refactoring the whole thing and not putting everything. That would be great to do. Yeah.
Great, thank you. Thank you for smoothly catching my bandwidth problems. Yeah, I imagine that if this technology becomes more accepted, more used, and more explored, then many things open and many of the designs, many of the assumptions will change. It will take a while to get there.
Yeah.
So you said this technology started like 10 years ago. So it's been thoroughly researched, thoroughly adapted to. on your post, you mentioned it's used by Signal, for example.
Yes.
I think it's for contact sharing or something like that.
Yes.
It's interesting that's been for a while, and many attacks have come and they have been patched, and it has also shown the limitations of relying on Intel for these things and on relying on the cloud provider to not perform very advanced side channel attacks. Can you tell us a little about the history of this, like the biggest problems you have seen and how you see it evolving to solve those limitations?
That's actually a question which needs a session for its own, I would say. Like I need really to prepare for, but I can tell you like SGX. So you mentioned like these TEs are all thoroughly researched. I wouldn't say that. I mean, mainly SGX was mainly like got a lot of like research on top of it. But now with the recent release of TDX is basically it's still like new and still being under research, and probably there will be then attacks and maybe not. Let's yeah, we will see. But for SGX regarding the attacks, you mentioned they are being patched. That's true, but not for all. So we saw like for Spectre and Foreshadow, for example, these kind of attacks, they have been patched by Intel by providing micro updates. But there are also other hardware attacks that have been done, which basically you would require like a direct access to the machine in order to conduct them. So they become harder to conduct, but they are possible. Now the question is, now we are, as you said, we are relying trust then on the service, like the cloud provider, like that is running our like GX machines, not being tampering with them or applying these attacks on them, which is true because it will then ruin their reputation, which why we kind of put the trust on top of it. Like we wouldn't think that Microsoft would go to the data center and does some kind of hardware attacks, but we still need to find ways to prevent such like replay attacks that can happen, for example, and so on. I think there is also replay attacks that can happen from the software side. That's why there are defensive mechanisms such as ORAM that is there to prevent that. Or no, I think ORAM is for the page fault accessing and reading from the access pattern to like extract some private information. That's why there is ORAM for. So yeah, for the hardware attacks, I need much more time. Like I need more time to do like my research because I did this like 5 years ago, and yeah, I need to refresh my memory there. But yeah, this is mainly the point.
Thank you.
Now you are lagging, Leo.
Building blocks in
Sorry, Leo, can you
a
repeat? Because you hanged for a while now and just came back.
all right. Can you hear me now?
Yes.
I was saying that I don't like Intel and I don't like AWS, and yet it seems like a clear
I think you are lagging again.
space more, see where we lead. We have
Yeah.
a question here from
You
Mateusz.
you lagged again, sorry. So I'm so sorry, but yeah.
Yeah, I know, I'm sorry. Thank you. We're almost done. We just have here a question from Mateo saying, what is not private in TEs?
What is not private in TEs? Can you be more specific? What do you mean? What is not in TEs, or like what do you mean? Like, do you mean a threat model? Like what's not considered private and what's considered private? So that would make it more clear. But in general, what they define as private is the threat model that TE specifically protects against. If we are talking about SGX, we already covered that in the start. If we are talking about the VM solutions that we have, like for example, AMD, SCV, SNP, and Intel TDX, the trust model there is larger, so that their TCB gets bigger. Now it trusts the guest OS. It trusts the applications that are running inside that guest OS and your configuration. And like for example, in TDX, the TD module and so on. So basically now your TCB got larger from simple enclave inside your application process up to a big size of like a whole guest OS and all the applications running into it. So what is now considered trusted here is much larger, and what's not trusted is everything not included into this. So on SGX, all the other tenants or even other enclaves running on the same machines, they are not considered trusted from the perspective of your enclave. So you don't trust even other enclaves that are running in the like as subtenants in the same machine, unless you create like a TLS communication and do like local attestation between these enclaves. Then you can initiate trust with them, but then basically you would have to do this extra step. Yeah, I hope I was able to answer it.
He says, amazing, thank you. So I think so. It's been an hour since we started, so let's try to close here. Let's see if my bandwidth allows for this. Thank you so much. Thank you so much, Mo. This was very clear. The first step to understand this exploration. Next week, we will have Andrew Miller, a researcher at Flashbots, talking about the secure best practices, what we have to take into account when dealing with this type of hardware, the things that we have to observe with more care on the different trust models that this integrates. Then you mentioned also TDX, which is another technology from Intel that takes a different approach. It's a virtual machine what executes in the trusted hardware. So we will explore that. We are focusing our explorations there for a while. And we will want to explore also what other teams are doing in the Ethereum ecosystem with hardware, because this will involve decentralized root of trust, which we cannot do alone, and we cannot rely on Intel for that. Sounds like a very, very good use case for blockchain ecosystem. And there are tampering mechanisms, anti-tampering mechanisms. There are explorations with ASICs and with open hardware, open architecture like RISC-V. We will play a while with all of these things. Slowly building up the knowledge. Remember, you can participate in the forum collective.flashbots.net. If you have further questions, our team will be happy to receive you. If you want to collaborate with us on these executions, these benchmarks, and what we can achieve differently with trusted hardware, please talk to us, join us. Is there something else on your mind, Mo, before we close?
Yeah, I really hope that you enjoyed it, or at least come up with something today I learned something, which is good, always good. And yeah, I wish that we increase the knowledge in such a way we can basically in the future be able to even audit a new technology such as TDX, because currently it's just a new green field, and the more attention we get to it, the more we know how to audit such applications built on top of it. So yeah, happy to do it.
I learned, I enjoyed. I'm sure many more people did. Mateusz, are you there with us?
Yes, I am.
Would you like to tell us a little about your plans in your team? Where does this trusted execution fall on the plans of these things that we're building, the next step for PBS, Suave, and all the explorations in Flashbots?
Yeah, sure, of course. So TEs in general are a good compliant part to blockchains, just because there is a different trust model. We have different trust assumptions, and we can just complement blockchains features and what blockchains can do. with the features of SGX and in general TEs. And I think that's mostly what we've been exploring, basically with all of the products that we are designing for TEs. Yeah, Mo has already shown us the block building part, which is especially difficult to solve outside of just execution environments because blockchains themselves are just subject to negative externalities of MEV, and TEs hopefully will come to the rescue. Yeah, I think that's kind of it. We just put them together, you know, take the best of both.
Amazing. Super excited and grateful for the work. It opens so many things. I'm eager to see like open enclaves, open architectures, and ASICs doing specific things related to block building and different attestations that the blockchain requires. Fred, are you there with us?
Yes, I am. Hello.
Thank you so much for all your work with community and with organizing this setup. Any last words you would like to share to close this?
Yeah, thank you so much. I'm super excited to get this fantastic initiative up and running. That was a very fun introduction, Mo. Great job. Looking forward to the next sessions. Keep an eye on the forum for more content and more live streams coming up. Thank you, Leo, as well, for great emceeing.
Amazing. Thank you all. Keep an eye on the forum. Fred produces a newsletter with everything related to MEV and our work and the work of others collaborating with us in the ecosystem. So if you want to get informed of what's going on, that's a good place to start. And join us next week. We will announce the date and the time soon. Thank you very much. Bye.
Thank you all. Have a nice day.
Thank you. Bye.
Bye-bye.